Hello and welcome to a video on transformations of two parent functions. One of them is the reciprocal function and the other is the inverse square function. And these are going to serve as an introduction to rational functions. Okay, when there's a variable in the denominator, you get something that's a rational function, generally. Okay, we'll talk about the definition another day, but right now just these two we can easily define. The reciprocal function we've already talked about, that's y equals 1 over x. And the reciprocal, the inverse square function, by the way, this graph is supposed to go up asymptotic forever, but there's the equation of the inverse square function. And the only difference is that square. It does slightly change the shape of these two branches of the curve, but more importantly, it makes them positive. So, for example, any input that I bring into the inverse square function squares the denominator, so it would be a positive over a positive. So you're never going to be able to get a negative input there, hence the graph is all above the x-axis. So briefly, we're not going to go into all the properties of this, but the domain of the inverse square would be the same as the domain of the reciprocal function, from negative infinity to 0, not including 0, union with 0 to positive infinity. And the range of this would only be the top half, so it would be from 0 to infinity. Okay, so let's look at the first example is just a transformation of a reciprocal function. And so we want to look at this as the x plus 2 indicating a transformation that on the inner part of the function, and then the minus 3 would be on the outer part of the function. So in other words, this would take the function and move it to the left 2 units. And this would take the function and move it down 3 units. And when we do this with the reciprocal function, we really want to do this with first the asymptotes, or the intersection of the asymptotes. And so with the parent function, those asymptotes intersect at 0, 0. And so we're going to move that down 3 and to the left 2. So our new asymptotes will intersect to the left 2 and down 3, so right there. So it's going to be something, these are going to be our asymptotes of the transformed function. And in this first example, which is a fairly simple case, there is nothing being multiplied by the x, and there's nothing being multiplied by 1 over x. So there's no stretches of any kind, there's no reflections of any kind, it's just simply moving over. So while the parent function has the point, which is maybe not that clear here, but it's 1, 1, the transformation will have the point that's 1, 1 from the intersection of the asymptotes. So we're going to have a point right here. And while the parent function has the point 1/2, 2, 1/2, 2 is right there, this one would go 1/2, 2 from the intersection of the asymptotes. And while the parent function has the point 2, 1/2, this function will have the point from the intersection of the asymptotes over 2 and up 1/2, so right there. So this branch would look something like that. Remember, it's not supposed to cross the asymptotes, and the asymptotes have to be there in your graph. And then it has its counterpart on the other side of that intersection. And minimally, the points you should give me are these points right here, which is -3, -4 for this one. And this point right here is going to be -1, -2. Okay, let's look at another example. It gets a little bit more involved. All right, so in this example, this is going to be a transformation of the inverse square function. And at first glance, it doesn't look like that because there's an x squared in the numerator. And we can't have that when we're doing the transformation. So we have to start out by rewriting this. So we're going to rewrite this as x squared over x squared minus 3 over x squared. In other words, what I'm really looking at here is 1 minus 3 over x squared. Now, if I really want to write this as an inverse square transformation, I'm going to change it one more time as 1 minus 3 times 1 over x squared. Now, there's the parent function, 1 over x squared. It's being multiplied by a -3, which means it's going to vertically stretch and vertically reflect. And it's being moved vertically 1 unit up. Okay? So let's look at this as a transformation rule. And since the parent function is y equals 1 over x squared, we can see that what's happening to the y's is 1 minus 3y. So in our transformation rule, nothing's happening to the x because it's x squared just like in the parent function. So our rule will look like this. xy goes to nothing happens to the x, but the y will be 1 minus 3y. Now we just need to know what points to apply this to, and we're on our way to a graph. So the first thing is we want to apply it to that intersection of asymptotes 0, 0. So 0, 0, which is technically not part of the graph, but it is an important point that helps define the shape of the graph, will go to 0, and then 1 minus 3 times 0, which is 1. So now we know where the asymptotes intersect. Let's just put those on here. 0, 1 up here. So in other words, it didn't move horizontally, but it did move vertically. That's the moving part. Okay? Now let's look at some specific points. Now on that parent function, we've got the point 1, 1. We've got a lot of the same points here. We've got the point, now if you put a 1/2 in here, you get 1 over 1/4. So you've got the point 1/2, 4. It's kind of hard to see it on here, but you've got the point 1/2, 4. Just think about that. Again, if you plugged 1/2 into this parent function, you get 1 over 1/4, which is 4. And you can see it on the graph too. All right, let's put that point in our transformation rule. So we put 1/2, 4 from the parent function. 1/2 doesn't change. 4 will be 1 minus 3 times 4. That's 1 minus 12. That's going to go all the way down to -11. So this function is going to be stretched quite a bit because of that 3. And it's already a square function, and that 3 is going to make it even more pronounced. All right, another point that's on here, what happens at 2? Well, at 2, when the input is 2, the output would be 1 over 2 squared, or 1/4. So there's the point 2, 1/4 on the parent function for the square. And so we're going to use that point 2, 1/4. And we're going to plug it in here. So when we plug it into our transformation rule, we get 2 for the x, nothing changes. And for the 1/4, we get 1 minus 3/4. 1 minus 3/4 is 1/4. That one's a little bit easier to graph. All right, let's see what we can do with this as far as just plotting these points that we have so far. So we know that we have 2 comma 1/4, we'll just put that right about there. All right, one thing we definitely don't want to skip is that the main point, one of the main points on here is the 1, 1. We didn't put that one in there yet. So let's put the 1, 1 and see what happens with that. So we get 1 doesn't change, and then 1 minus 3 times 1 is 1 minus 3, or -2. So we have the point 1, -2 right there. Okay, let's see if we can get that other point sort of imagined, even though we can't quite get this on here. 1/2 -11 is way down here. So it's going to be something like this. And it's asymptotic here, so it's going to have to continue. If you want to get another point there to see it, never hurts. Put in a calculator to check it. That doesn't hurt either, as long as you have a calculator available to you. And that's sort of what that one branch looks like. The other branch will be on the other side. It's maybe a little bit hard to see that, so maybe we should get a point here. And let's see what happens to -1, 1. Oh, let's just kind of take a look over here. -1, 1. Definitely on there, right? So let's get that point. So -1, 1 would go to -1, and then 1, same output, so it's going to go to -2. If we didn't make a mistake last time, let's just check it. So we have 1 minus 3, right, if we plug in a 1. 1 minus 3 is negative 2. All right, so we have negative 1, negative 2. Negative 1, negative 2 right there. So we do have a counterpoint, like it's reflections on the other side. This is an even function. We can now use that even property if we think about it, and we can get this point right here as well. And we can get a point way down here that will be at, since 1/2 negative 11 is there, so will negative 1/2 negative 11 be there. So we're looking at something like this. Okay. Vertically stretched by a factor of 3. You can see that stretch going down here. A couple of key points. Well, we've got them here, so you don't need to write them in 2 places if you've already got them, but we've got the point 1, negative 2, negative 1, negative 2. We've got the point 2, 1/4, negative 2, 1/4. And we've got the point 1/2, negative 11. And we've got the point negative 1/2, negative 11. Okay, let's look at another example. Okay, so let's look at this one. Take a minute, see if you can break it up so that there's no longer an x in the numerator, and see if we can figure out what the transformations are in this. Okay, so for a problem like this, once you can see it as a transformation of that parent function 1 over x, it becomes much easier. All this is doing is moving that parent function down 1. So this is the reciprocal function, this one right here, just being moved down 1. So we want to move the intersection of the asymptotes down to here, and then just fill in the pieces. It's much easier when there's no stretching involved, and I'm going to let you guys try this one, and then I'll just show you what it looks like. Okay. So there's our transformed reciprocal function. Everything moved down 1. This parent function has a point 1, 1 moved down to 1, 0. 2, 1/2 moved to 2, negative 1/2. Everything moved down 1. 1/2, 1/2, 2 went to 1/2, 1. Everything moved down 1. All right, let's try the next one. Okay, so this is a transformation of the parent function y equals 1 over x squared, similar to example 2, except this one has no stretching of any kind. It's just moving it and reflecting it. So take a minute, see if you can come up with a transformation rule, and then we'll look at this together. Okay, so there is the transformation rule. Now you might look at this 1 minus x and say, wait a second, how can 1 minus x go to 1 minus x? And just a quick reminder here of how to find the inverse. If y equals 1 minus x, you switch x and y, solve for y, you get the same thing. Graphically, you can see that the line y equals 1 minus x is in fact a reflection over the line y equals x. So it fits the definition of an inverse of itself in every way. All right, so that's going to be our transformation rule, and we're just going to apply that now to some key points. So we have the intersection of the asymptotes, 0, 0. We definitely want to see what happens to that. We have the point 1, 1 and negative 1, 1. Those are each on the reciprocal function, the inverse square function. If we plug in a 1/2, and we saw this on the other example, but if we plug in a 1/2, we get 4, right? 1 over 1/4, which is 4. If we plug in a 2, we get 1 over 4, 1 over 2 squared, which is 4. Let's see what happens with those points. All right, so there's our important points here. Remember that this one is the intersection of the asymptotes. So I put that down already. And now I'm going to put the asymptotes on there and then plot the points and see what we get. Okay, so you can see these points, the 3 points that are on the left side of the vertical asymptote reflected over, and that 1 point that's on the right, that was this one, also reflected over. Okay, let's piece them together. And there's the graph. Again, you don't have to put the points on the graph if you have them right next to the graph. I hope you found this helpful.